In this video, we're going to be introducing some basics of circles. First, we're going to start with parts of a circle that can be created using lines or segments, and then we'll get into a couple different types of angles that can occur inside a circle, and we'll also talk about some arcs. So first, let's talk about these parts of a circle using lines or segments here. So in this diagram, we have a few different types of things happening. This line BD is intersecting our circle at two different spots. That's called a secant line. This other line on the outside of the circle, line JB or BJ, is touching the circle at one spot. It's actually touching at point H right there. If a line touches a circle once as it crosses it, that's called a tangent line, and that point at which it touches is called the point of tangency. So point H is our point of tangency, and line JB is our tangent line. A is a point located at the center of the circle, so that's what we call that point. Segment HF here is a segment running through the center of the circle, and it stretches from one end of the circle to the other. That's called a diameter. And this segment right here, segment DG or GD, is a segment in the circle that does not go through the center, but it still goes from one side of the circle to the other. That's called a chord. And actually the diameter is what's known as the longest chord, but we don't call it a chord because it has a special name. We call it the diameter. So if a chord goes through the center, it's called the diameter. If it's not going through the center, we just call it a chord. And then lastly, if you take a piece of that diameter, stretching from the center of the circle to the outside in either direction, but just half of this diameter here, that's called the radius. So the radius is always half the diameter, or if you double the radius, you get the diameter. And there's not just one radii. We could say there's another radius over here. We could have a radius stretching from anywhere in the circle as long as it comes from the center to the outside. We call it a radius. So even though we normally just refer to one radius, there is basically an infinite amount of radii inside a circle. So there's some basic parts of a circle. Next, let's talk about these things called arcs. Arcs are just pieces of our circle. So they are curved lines or curved segments. I would prefer to call them a segment because they definitely have a beginning point and an end point here. So a curved segment. We can actually combine measures of arcs, and we can talk about their measures in degrees. There is this thing called the arc addition postulate, which is similar to the segment addition or angle addition postulates. This basic concept that we can take two smaller parts and combine them together to create a bigger piece. So if I take this small arc from A to D and combine it with the arc from D to B, then essentially I've created this whole big arc from A over to B. So if I know the total and I know a piece, I could use subtraction and solve for my missing piece, or I could use addition and combine my smaller pieces to get my total big piece. So the copy is a little light here. I'll try and interpret what this is saying here in this example. Given a few different statements here, let's add it to the picture here so we can visualize it and see what we're looking at. Given an angle measurement for angle BCD equal to 30 degrees, find angle BCD here. And we're going to call it 30 degrees. As it turns out, this angle right here with its vertex in the center is called a central angle. We'll describe this a little bit more on the next page, but we kind of need it to solve this problem. This central angle here, its measure is actually equal to the measure of the arc on the outside. And so this arc is really just measuring the gap between those 2 points. And so of course it's going to be equal to this angle with its vertex in the center of the circle. Next statement, we're told that the arc from E to F is equal to the measure of 61 degrees. So over here we have arc EF. So we could say that that little arc is 61 degrees, but as it turns out, this corresponding arc is also 61 degrees, and this central angle right here is also 61 degrees. Then we're told that lines AE and BF intersect. So lines BF and AE are intersecting. Intersecting lines will always create vertical angles. So we have this vertical pair right here. Congruent angles. So if this angle is 61, its vertical pair over here is also 61. So if that central angle is 61, then its corresponding arc out here is also 61 degrees. And then lastly, the question is asking us to determine the measure of the arc from A to B to D. And so sometimes with our arc names, we use 3 letters because that'll give us a better description of where the arc is. If I just called it arc AD, I don't know if I'm talking about this major arc over here or if I'm just talking about this minor arc right here. So sometimes we involve a 3rd letter to help us out. So we want to find the measure from A to B to D on this arc. Well, we know that part of it is 61 and another part of it is 30, so if we just combine those pieces, we should get our total arc length of 91 degrees. All right, so let's emphasize that idea that central angles and their corresponding arcs, or as they're sometimes called intercepted arcs, have an equal measure. So central angle is equal to the intercepted arc degree measure. And in general, central angles are angles that are describing something that measures less than 180 degrees. So we would never call a major angle over here a central angle. All right, so central angles will always have their vertex at the center. That's why they're called central angles. And their measures are always equal to their intercepted arcs or corresponding arcs here. And you will always be able to recognize that because the angle is going to hug the arc that it corresponds with. So if we're asked to solve for x or the measurement of angle AOB, the exact same question. This arc is 82, so its central angle would also be 82 degrees. We can think about that backwards. If we know the central angle measure and we're asked to find its corresponding arc measure, well, we know it's going to be equal. So if the central angle is 140, then the corresponding arc measure is also 140. More of the same, just a little bit more challenging on this example. Again, we're given the central angle here measuring 50 degrees, and we're asked for the measure of its corresponding arc from M to N, so it's going to be the exact same, also 50 degrees. Over here on this central angle, we have a right angle given to us by this symbol right here. So we know that measure is 90, and its corresponding arc that it hugs is also going to be 90 degrees. And then lastly, we're asked to find the measurement of x, which is actually this angle on the other side. So that angle is going to correspond with this arc measure out here. And if you know that a circle measures 360 degrees, then we just have to subtract the arc measures that we already know from 360. So we already know 140. Take that away from 360 and we're left with 220. So this arc over here is going to be 220, meaning that the angle around the vertex is going to be the exact same, 220 degrees. Another type of angle that we can have in a circle is called an inscribed angle. And again, the copy is a little light here, so I'll interpret that for you. An inscribed angle is going to be an angle that's created by 2 chords. So we got 2 segments not going through the center of the circle, creating an angle where the vertex is on the circle. So it's not in the center anymore, now it's on the circle. So the corresponding arc is quite a ways away from that angle. So there's going to be a different relationship here between the arc and the angle. As it turns out, the angle, the inscribed angle measure, is going to be half of its corresponding arc. And then if you think about that backwards, you would double your angle to get your arc. So the arc is twice the inscribed angle. Let's play around with that concept. Here we're given an example where the arc is 82 degrees, and we're asked to find its corresponding inscribed angle measurement. So that's going to be half of our arc measurement, making the angle 41 degrees. Over in this example, let's start off by finding angle ADB. which again is going to be half of its corresponding arc up here, so half of 76. Means that our angle is going to measure 38 degrees right there. And then next we're asked to find the arc length from D to C, which is going to be double the inscribed angle. So given the inscribed angle, we're going to double that to get its corresponding arc measure. So 45 times 2 is going to be 90 degrees. So this arc measure is 90 degrees. One more example to play with. This time we're going to need to know a little bit about central angles and inscribed angles together. Given the measurement of angle ABD is 40 degrees, here's our angle ABD, so we're given the inscribed angle measure. Well, what we can do with that is double it to get the arc measure that it corresponds with, or hugs here on the outside. And then we can work backwards from there. We know that the central angle, which is what we're asked to find the measure of, is going to be equal to its corresponding arc. So the angle ACD measures 80 degrees. One more thing to describe here. There is a special case involving inscribed angles. If an inscribed angle is created by using the ends of a diameter, it will always create a 90-degree inscribed angle. So taking the ends of the diameter to create an inscribed angle, it could be anywhere on the circle, it doesn't matter, it's always going to create 90 degrees. So in knowing that, then we can start to see how we can have inscribed triangles, specifically right triangles. And knowing your properties of right triangles may help you in solving some of those types of problems. So again, here we're given the diameter and one of its ends, and then we're asked to solve for a few different measures here. So we'll see how we complete this and create that 90-degree angle here in a sec. First, we want to find the measurement of arc BC. So again, let's go back to that diameter. If we can make a diameter or see a diameter, then that cuts our circle degrees in half. So if our total circle is 360, then half a circle must be 180. And so here we know that we have 92 degrees of it, and we need to finish it off to add up to 180. So use subtraction to figure out what's missing. And we're missing 88 degrees on that half of the circle there on the outside of the arc. Then that allows us to solve for x because that arc is going to correspond with this inscribed angle, the measurement of x. So if we take our arc and divide it in half, we get our inscribed angle measure of 44 degrees. And then we're asked to find the measurement of angle ABC. So we actually have to draw the other side of our angle here. Connect B to C, and then notice that we're connecting the ends of a diameter to create an inscribed angle, so we know that angle there at angle C is going to be 90 degrees. And so because we know 44 degrees and 90 degrees in our right triangle, we can use the property of triangles to figure out the missing angle there. Or we know that in a right triangle, these two angles are complements, so we could simply subtract what we know from 90 to get our missing piece there. And then also a third way that we could do it is seeing that this arc right here measuring 92 degrees is the intercepted arc of this inscribed angle that we're asked to solve for. So all we would have to do is cut that arc measure in half to get that inscribed angle measure. So regardless of how we do it, we get 46 degrees. So there's some basics to circles, arcs, central angles, inscribed angles, and some of those segments and lines created when playing around with circles.